Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A level. This is Chemistry for January 2021, Unit 5. I will do the Section C. And again, I have already done the video for Section A as well as Section B. The links to these videos will be put in the description box below this video. So let's begin with the question. It says, this is question 24. There are over 1,000 chemical compounds in coffee, and their physiological effects are the subject of considerable speculation and research. The verdict on coffee is contradictory. Some of the compounds have been identified as toxic and even carcinogenic, but others are antioxidants associated with cancer prevention. Recent research has identified compounds in coffee that might be used in the treatment of prostate cancer. By far, the best-known compound in coffee is caffeine, the most widely consumed psychoactive drug in the world. In small amounts, it is a stimulant, but doses in excess of 10 grams per day are toxic. Caffeine contains amide and amine groups. So let's continue down here. You can see this is the structure of caffeine. Then going down, they say, chlorogenic acid is responsible for the acidic taste of coffee. It is an antioxidant and has also been shown to slightly decrease blood pressure. So again, here we have the structure of chlorogenic acid. Then they continue to say caffeic acid, quinic acid, and acetoin are also present in coffee. So let's continue to the next page. They say, another way of drawing the structure of caffeine is shown here. So this is another way to draw. Remember previously there was no ring in here. Again, to take you back slowly. This is the structure of caffeine they gave us previously. You can see there is no ring. There is a double bond here and a double bond here, but no ring. So to take you back where we were. So this is the other way caffeine can be drawn. And then they go on to say, the bonding represented by this diagram of caffeine differs from that given in the passage. Explain what this diagram indicates about the bonding in caffeine, stating the effect on the structure of caffeine. So it means because there is a ring here, yet the previous structure just had either carbon-carbon double bond or carbon-nitrogen double bond, it means this ring is showing delocalization of electrons, and the only reason for this delocalization is due to the lone pair on the nitrogen being incorporated into the ring, causing delocalization to occur all over, and therefore the ring structure is going to be shown. So in this case, I have to reason using the chemistry of benzene. So I say there is a ring which indicates the localization of pi electrons in the structure. Of course, so any pi electrons in here are delocalized. Some of these, basically, they are delocalized. Those present in the carbon-carbon double bond. And then I went on all carbon-nitrogen double bond. So I went on to say this delocalization includes the pi electrons of the double bonds and the lone pair on nitrogen. Yes, nitrogen atom has a lone pair. That lone pair, along with the pi bond electrons, are incorporated into the ring, and that is due to the delocalization that occurs. Then I went on to say, due to the ring formation, the carbon-nitrogen bonds and in the ring structure will have the same bond length. Again, let's see. This is a carbon bond, a carbon, and a carbon. So no matter what, provided we have a ring structure in here, it means this bond is equal to that bond, which is equal to that bond, and that is equal to that bond. All carbon and nitrogen bonds are going to have the same length due to the ring structure formed. And lastly, I say, due to the ring formation, the ring structure will undergo substitution reactions, but not addition reactions. And again, if you're a student and you're wondering how would you know all this? This is referring to the chemistry of benzene. You remember in the structure of benzene, let me try to draw it for you like that. We have a ring structure, and because these are all carbon-carbon bonds, they're carbon-carbon, all these carbon-carbon bonds have the same length because of that localization of the pi electrons within the ring or within the benzene. So bond length is identical in all carbon-carbons, and then that is why. And also, we remember that benzene goes through addition. It doesn't go through addition reactions, but it goes through substitution reactions where electrophiles substitute the hydrogens. So the last part here is said, due to the formation of the ring structure will undergo substitution reactions, but not addition reactions. So let us continue down here. The next part says, suggest why caffeine is a much weaker base than a primary amine such as ethylamine, even though the right hand ring has two amine groups. Again, this is the same reason. Remember that nitrogen has a lone pair, and if that lone pair is incorporated into the ring, yet this nitrogen atom is the one that is going to aid the structure to be a base by donating that lone pair. The incorporation of this lone pair into the ring due to leading to delocalization makes this lone pair not readily available, and therefore it's not going to be easily donated to to form the reaction easily. That is why it's not going to be a strong base. So I say, in caffeine, the lone pair of electrons on the nitrogen overlaps with the pi electrons, and it is incorporated into the ring, correct? And this reduces the electron density on the nitrogen, making caffeine a weaker base. However, in ethylamine, there is an ethyl group. Ethylamine, there is going to be an ethyl group. Let's see, CH3, CH2, NH2. This ethyl group is electron donating, and due to that, it increases the electron cloud or electron density around the nitrogen, making it a stronger base because the nitrogen is going to readily donate those electrons in any reaction. So let's continue to the next part. Part B says, a 200 centimeters cubed cup of coffee contains approximately 85 milligrams of caffeine. Roman 1 says, calculate the concentration in mole per decimeter cubed of caffeine in this cup of coffee and give your answer to an appropriate number of significant figures. So I began off by drawing my structure. The reason for this is I wanted to find the molecular formula of the whole structure, which is this. I found there are 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens, as you can see them all here. So once you get this, you can be able to find the molar mass. Just multiply through and add up to find the molar mass, which is 194 gram per mole. Let me put here gram per mole. So after finding that, I now know the molar mass. So I need to find the mass. Since I was given 85 milligrams of caffeine, this mass is in milligrams. I have to find a way of converting milligrams to grams. But I know that 1 gram is equal to 1,000 milligrams. Therefore, 85 milligrams should equal to 85 divided by 1,000, which is going to be 85 times 10 power negative 3 grams. So this is the mass in grams. Knowing the molar mass and the mass in grams, I can be able to find the number of moles of caffeine. So moles of caffeine should be the mass in grams divided by the molar mass, which gives me that, which is 4.381 times 10 power negative 4 moles. And then, since I know the number of moles, I can use them to find the concentration because I was given the volume. The volume was given to me in centimeters cubed. I have to find a way of converting that volume to decimeters cubed, and you do that by dividing by 1,000. So, if you see here, this is volume in decimeters cubed, and that is the number of moles in mole. When you divide that, you get this as the answer. And then when I remember they told you to give your answer in appropriate significant figures, I gave 3 significant figures, which is 0.002 mole per decimeter cubed as my answer. So let's continue next. The next part says the removal of caffeine from the body is a first order reaction with a half-life of between 3 and 7 hours for an adult. Remember they've said 3 and 7 hours, so this is minimum and that is maybe maximum. So they say an adult drinks coffee containing a total of 160 milligrams of caffeine. They say calculate to the nearest hour the minimum time needed for the amount of caffeine in the body to drop to 20 milligrams. Now remember the beginning is 160 milligrams. So if we're talking about half-life, it will take half-life to convert 160 to 80, the next half-life to convert 80 to 40, and the next half-life 40 to 20. If there was a 10, it would take next half-life from 20 to 10. So basically, the time it takes for the initial mass to be divided to half its original mass, that is going to be the half-life. So in this case, remember they said minimum. It goes from 3 to 7, and here they're asking for minimum. So the minimum half-life should be 3 hours. So here it's going to be, this is the first half-life, the second half-life, and the third half-life. Since each half-life is 3 hours, you add everything up, it gives you 9 hours. So it will take 9 hours for 160 milligrams to be broken down to 20 milligrams of caffeine. Let's go to the next part. This part says chlorogenic acid is an ester of caffeic acid, a compound that is present in all plants. So this is the structure of caffeine, as we can see, caffeic acid. So in caffeic acid, you can see this was a ring containing two OH groups, and some structure was attached through a specific reaction. So they're going to say, as students suggested, that caffeic acid could be synthesized by an electrophilic substitution of 1,2-dihydroxybenzene. This is the 1,2-dihydroxybenzene minus that part. So they say, draw a mechanism of this electrophilic substitution, including the formation of a suitable electrophile. Now, if you look at this whole structure, since this is the 1,2-dihydroxybenzene, it means this is the structure that was added, or the electrophile must have been this. So I chose a Cl atom, so that attached to Cl. So this is going to be my suitable molecule that I'm going to use to get the electrophile. So that is exactly this. When I react that with aluminium chloride, I will get, so basically this is acylation. I will get HO, CO, and then the carbon and the other carbon. There is a plus because this is the electrophile generated, and the other is the intermediate part, which is going to be used to regenerate the catalyst. Again, in this case, aluminium chloride is the catalyst. So in the first step, the electrophile is going to attack the ring, and then the ring is will donate electrons to the positive carbon in the electrophile. And then in the next step, we can see the ring opens up facing the side where the electrophile has attached, and then the hydrogen bond is going to be exposed. So in this case, we can see, please remember to position it like that and put a positive. This open end should be facing the part that has received the electrophile. Then in the next step, the hydrogen bond will break, returning the electrons into the ring, and we will get a circular structure one more time, or it will be ringed, and then the hydrogen that has been lost, in this case, will be here. And finally, this hydrogen, finally, this hydrogen will react with this one in order to regenerate the catalyst and produce HCl as the byproduct. So let's continue to the next part. Deduce the structure of quinic acid, which combines with caffeic acid to form chlorogenic acid. So here they've given us the structure of caffeic acid, and they've given us the structure of chlorogenic acid. As you can see, if you want to deduce the structure that is going to be reacted with this one to produce these, we have to look at the product and find the missing part. If you look at the product, we have this OH, we have that OH. So basically this whole structure, this until about here, is present in the other side. So again, let me try to remove this. Looking at the structure, we can see that this here is present the other side. It's basically that. So the combination or the connection between the two occurred about here. Now, since this part looks like the carboxylic part or the previous carboxylic group, this product is an ester, it means that should have been an alcohol group. So the structure should just be exactly, let me get a different color. The structure should be exactly this, but add a hydrogen onto here, like that. So it should be an OH group, which is an alcohol. Remember, to form an ester, you can produce it from a carboxylic acid and an alcohol, or an acyl chloride and an alcohol. But for me, I chose the alcohol this side because that's what they were asking for. They did not ask for the carboxylic side. They were looking for the alcohol part, so this is the part here. The hydrogen had to be added here to create the structure that would have been used in the formation of the ester. So quinic acid has an OH group here. I hope you guys understood it clearly. The carboxylic part, the alcohol part combined form an ester. So where the bond, the ester bond is linked, or where it forms, one part should be carboxylic and the other part should be an alcohol in this case. So let's go to the last part of this section C. It says, the structure of acetone is shown with one of the proton environment labeled. So we have this environment labeled here, and they told us it's environment A, this one here. So of course, the structure was not like this. Let me take everything away. It was like that. Okay, that is how it was, and they told us this is the first environment. So since you guys know this is a methyl group, I always like to position the hydrogen so that there is no mistake to be made. And this is a carbon as well, carbon, so that is also methyl, as you can see. So Drawing the structure like that, we can see there are, let's see how many proton environments. There is this environment here, there is this proton here, so there is that proton and there is that environment. So environment, that environment, this environment, this environment. So if this is A, I can call that B, I call that C, or that D. And again, depending on how you've called it, because I erased what was previously there, let me see if I can bring it back. A minute. Try to bring it back, the part that was there. So because I labeled it based on the, I labeled this part here based on the information I had put previously. Okay, we have it. It's right here, this part here. So I call this A, that is what I called B, that is what I called C, and that is what I called D. Remember, the next question is going to ask us about the splitting patterns and the environment. So let me first go to read this part. They say, identify the other proton environments of acetone on the structure and label. So there is environment A, which was given to us, environment B here, environment C, and environment D. All those environments are unique, they're different, they're not the same, and they have protons in them. Then Roman 2 says, complete the table to show the splitting patterns in a high-resolution Proton NMR spectrum of acetone. Remember they said high resolution, so there should be splitting if possible. So let's see. This one here is going to be split into a singlet. The reason for this is the neighboring carbon has no protons on it, so it's going to be a singlet. Let's see another one. This environment here is going to be a singlet as well because, this one here, give me a minute. Environment D is a singlet as well because the neighbor has nothing, then it doesn't have a proton. And then this environment here, we can see environment C, it's going to be a quartet because the neighboring carbon has 3 protons. So using the n+1 rule, it's going to be a quartet. And that environment there is going to be a doublet. The reason for that is the neighboring carbon has 1 hydrogen and 1 + 1 creates a 2, so we call it doublet. So the environment A is a singlet, environment B is a doublet, environment C is a quartet, and environment D is a singlet. So this brings us to the end of section C of this paper. Thank you so much for watching this video and for being with us. Please do not forget to subscribe to our channel. And as I said previously, I will put the links to section A and section B of this paper in the description box. Do not forget to check them out. See you next time. Bye-bye.